Okay, hello everyone. Thanks for having me here. So my name is Jelle Metz, and I'm from Leiden Observatory, and I am working on deblending galaxies for an upcoming weak lensing survey. So that's a bit more upstream from what we've been talking about the past hour. So what is deblending? Well, specifically, that's in this case, for instance, where we have several galaxies which partially overlap, and that's because of the projection effects, of course. When we observe them. And they can influence both our photometry measurements, which are important for the photometric redshifts, and also they influence the shape, and therefore the shape and the shear measurements. I often compare this to like a few beers at a long table, where if you want to determine all the types of beers that people are drinking, you want to look at the color, but also at the shape of the glass. And the beers are partially translucent, just like galaxies, so you can see part of the light behind it, and you can also have like a prior on the shape estimate of the beer glass. And this will be quite important for our upcoming surveys, especially for LSST, because LSST will go to very deep, very low, very high magnitude, to 27, and will have quite a large PSF, so a lot of galaxies will be blended in that way as well. We go up to almost 50% blendedness. And so if you don't take this into account, you have a huge effect on the weak lensing measurements, and you should either throw away these samples, or you should handle them some way that you can still use them. And throwing away half of your sample and having such an expensive telescope is not ideal. So there are some existing methods for this. For example, the variational autoencoder, where you input a galaxy, a single galaxy that's simulated with some noise, put it through the autoencoder, and then you get a prediction out again. And then in this way, your latent space describes the morphology of the galaxies. If you then go to the next step and you give it blends and freeze the decoder, then your encoder knows how to give the latent space parameters that produces the single galaxy in the decoder. Well, if we look at this latent space, it contains a full description of the blend. So if we give it our training data, and then we compare that to some test data, where we have a different set of galaxies, for example, an outer distribution set, the OOD set, then we can plot our distribution in our latent space. It would look something like this, where you have one contour and another contour, and they don't fully overlap. If you use the likelihood ratio then, and you draw for one sample, then you can determine, in essence, whether your sample is from the in distribution or outer distribution set. So this is what it would look like. It's a bit messy, but there's a large dimensionality. It's not a curse, but a blessing, actually, because the distributions partially overlap, and if you go to higher dimensions, you pull them apart. And in this way, with the likelihood ratio, you can quite accurately determine whether your sample is out of distribution or in distribution. So that's the new innovation here. So if you also look at other descriptors, not using an autoencoder, so for example, the CAS and the mid statistics for galaxies, then we see that the performance is a lot worse. So our autoencoder does describe the galaxy a lot better in this way. So we have here our Outlook. I'll leave it at this. And you can ask me any questions about this on Slack or in person. Thank you for your attention.
Thank you.